Hello guys, I'm Mahmoud. I will be your tutor for this section, for this session. We'll be talking about calculus, a session sponsored by the Chain of Education. In this session, we will be talking about infinite series. For your notes, should know that what we are talking about, what we started last time, was chapter 10 in Thomas' calculus book, and what we will be discussing today is section 10.2. So it's chapter 10 and section 2 from this chapter, which is infinite series. In this session, we'll be defining the infinite series. We'll be talking about geometric series, telescoping series, and the nth term test or divergence test. So what is an infinite series? We discussed in the last lecture that a sequence is a group of terms that is incremented, indexed, whatever you want, call it. So we can say it's A0, A1, A2, blah, 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 AN, and keep going on. We also discussed before that the improper integral is the act of the summation of rectangles that are very small infinitely. And this is how we can evaluate the integral to be convergent or divergent. And A0, A1, A2, AN happens to be a value that can be added and can be the area of a small rectangle. I don't know how small this rectangle is. However, I know that's a value. And mathematicians had in mind uses for summing these terms infinitely. So I'm saying is that what if I want to add the first term with the second with the nth term and so on? This will cause me trouble because sometimes this could be a constant, and we've seen that in the convergent integrals. Sometimes it could be plus infinity, and we already seen that also, or minus infinity. In all cases, I know that if I took a partial sum, I mean by a partial sum, I took the first n terms, okay, n terms, called Sn. So, and kept the remaining terms. I know if this is a convergent, so if the first n terms add up to some constant, then the whole series would be convergent. Otherwise, it will be divergent. So an infinite series is the summation of terms of a sequence. And we can know its behavior by using the partial sum, the summation of the first n terms. And if the limit as n tends to infinity of this partial sum is equal to L, so see, as n tends to infinity, this means that the n terms I chose are infinite, okay, is equal to L. This means the whole sequence, the whole infinite sum is equal to a constant, then convergent, and otherwise it will be equal to plus or minus infinity, and it will be divergent. So the first infinite sum we'll be talking about is the geometric series. The geometric series is a very important series, and it takes the form a times r power n, where a is any constant and r is the ratio I'm multiplying by. So using some discrete mathematics and algebra skills, we can know that from n equal 1 to infinity, or n equal to 0 infinity in this case, that this whole infinite series will add up to the first terms times 1 minus ratio power n over 1 minus r. This means this is equal to the partial sum. Oh, sorry, So this is not infinity. N. Okay. This is equal to the partial sum Sn. So now limit of Sn as n tends to infinity is dependent on R. Why? Because we discussed before that if we have a geometric sequence, a power function, if the value of R is less than 1, then this is convergent, it goes to 0. And if it's greater than 1, it's divergent, it may blow up to plus or minus infinity. And if it's equal to plus or minus 1, it's inconclusive. Type. In this case, if R is less than 1, sorry, oh, here is not N, it's R. If R is less than 1, what will happen? This will be equal to A0 times 1 minus, this will be 0. So A times 1 over 1 minus R, which is some constant. And in this case, the whole infinite sum will be equal to a constant, then it will converge. In other cases where R is greater or equal to 1, this R power n will evaluate to be infinity, and hence the whole series will diverge. In case of R equal to 1, okay, so we have the summation of A basically from n equal 0 to infinity. It's the summation of A infinite times. Of course, it will be equal to infinity, and of course, it will be divergent. And in case of R being minus 1, this will be the topic. No, actually. So I will have minus A plus A. So whether I'm starting from an odd term or even term, this will be 0A or A to A. So at infinity, this will be the summation of the series will not exist basically, and the series will be divergent. Okay. So the second important form of series, special series that we're talking about, is the type of infinite series that its initial terms, cancel in some way, cancel. Okay, and as and the partial sum presents itself to us in some way that we can use, we can evaluate, we can calculate its limit. The same way Sn was equal to A0 times 1 minus R power n over 1 minus R. Here we are trying to find this Sn. Okay, I will solve this first example and I will keep the second example as an active exercise for you. Okay, so in the first example, we have the infinite sum from n equal to infinity of ln n plus 2 over n plus 3. So here, whenever you see consecutive terms, n plus 1, n plus 2, n plus 1, n plus 4, no matter what, n minus 1, n plus 7. Whenever you see consecutive terms, this means we can use the telescoping series. This means that the series we are dealing with have high chance of being a telescoping series. Okay, let me tell you why. So, you see, this could be written as from n equal to infinity, ln n plus 2 minus ln n plus 3 using the log property, right? Okay, so what does this mean? That upon evaluating terms, look what will happen. So first for n equal to, I will have ln 4 minus ln 5. Then I will have ln 5 minus ln 6. Okay, wait. Those two cancel. Those two are 0, right? So I will have here ln 6 again minus ln 7, and those two cancel. So it keeps going on and on. So until I reach ln n plus 2 minus ln n plus 3. and ln n plus 2 will already be existent here, so it will also cancel here. So what I will be left with is, so suppose here we are calculating the partial sum because we stopped at the nth term, is ln 4 minus ln n plus 3. Okay, so this means that this whole partial sum is basically ln ln 4 minus ln n plus 3. Okay, and this is cool. I can know the limit of the partial sum as n tends to infinity. And in this case, it will be equal ln 4 minus limit ln n plus 3 as n tends to infinity, and will be equal minus infinity. This means that this whole series is divergent. Okay, I will leave the second example for you as an active exercise. Try solving it. It's very nice. You may use the partial fractions property we discussed before in chapter 8. The last test we will learn about today is the nth term test or the divergence test. We've seen that test before. If the limit of an is not equal to 0, this means that the infinite term I reached is not equal to 0. This means that I've been summing for infinity and the infinite term is still summable. And hence, whatever the limit is, the series will be equal to plus minus infinity. Okay, and hence the series will diverge. And another thing to keep in mind is that if it's equal to 0, the test is inconclusive. The divergence test fails if the limit of an as n tends to infinity is equal to 0. That's all for today. Study well. I hope you enjoyed the session. See you in next session. Oh, sorry, I will not see you. I hope I can. I will attach an exercise sheet for these sessions soon.